Good afternoon. It's my great pleasure to welcome you at the occasion of the 170th Qatar Lecture. For those of you who, it's wonderful that it's so full. It gives me great enthusiasm for epidemiology. If you want to sit, you can go to an overflow room. This is G2, close by. I see nobody wants to go. Everybody wants to stay here. I understand this very well. I would do the same. The Qatar Lecture, Preventive Medicine, has been presented once or twice a year since 1912 under the bequest of John Clarence Qatar, a graduate of Harvard Medical School. It is the oldest lecture series of this kind in epidemiology worldwide, and it has been since 1912 indeed given under the auspices of the Department of Epidemiology in what is now the Harvard Chan School, the oldest department in this school. Now, before we go to today's Qatar Lecture, I would like to take you back 100 years. In 1919, the Qatar Lecture was given by Alice Hamilton, the first woman professor at Harvard, industrial medicine, and in our, at that time, combined Harvard Medical and Harvard School of Public Health. Since then, in total, this is 170, remember, today, 10 women have given the Qatar Lecture. 6 of them in the past 15 years. And I would like to particularly have your attention for the 4th woman Qatar Lecture. This was in 1997. It was Lee Nelken Robbins. And so I think this is the first degree relative Qatar Lecture that we have. Wonderful, really wonderful. The laudatio of today's Qatar Lecture will be given by Professor Miguel Hernan. Miguel is the Colocotrones Professor of Epidemiology, both in the Department of Epidemiology and Biostatistics. It's a distinct honor for me, Miguel, to ask you to come here now.
Consider this question. Have you ever met a true genius? For anyone who knows Jamie Robbins, the answer is obviously yes. And since I cannot provide an exact definition of genius, other than you know it when you see it, I've recently asked several people about their experiences with Jamie. And let me give you some typical answers. A 10-minute conversation became an unforgettable intellectual experience. A passing comment by Jamie turned out to be the solution to one of our hardest problems. I felt like someone has turned on the lights inside my head. If that isn't genius, I don't know what it is. What Jamie Robbins has contributed to causal inference is as hard to exaggerate as the role of causal inference itself in science. Before 1986, there was very little attention paid to the causal effects of treatments that vary over time. And Jamie concluded that the situation was absurd because most or many questions in public health and medicine are actually about treatments that change over time. Think of medical treatments or screening, air pollution, diet, you name it. So in 1986, Jamie published the first formal counterfactual theory of the causal effects of time-varying treatments. Before then, there were no statistical methods to estimate that type of effects. Jamie's paper brought us the G formula, which was later rediscovered by artificial intelligence investigators and was confirmed to be the most general algorithm for causal inference. During the next decades, Jamie went on to develop, with Andrea Rodnitsky and others, semi-parametric alternatives to the parametric G formula. And those methods, inverse probability weighting of marginal structural models, G estimation of structural nested models, doubly robust methods, are now the methods that dominate the literature in causal inference for time-varying treatments. Jamie also played a key role in the development of causal graphs to describe the assumptions that we make in causal inference. And his work has led to the development, with Thomas Richardson, of SWIGs. SWIGs are a new class of causal graphs that are destined to become the standard graphical representation for causal inference in this century. Almost single-handedly, Jamie put causal inference from complex longitudinal data at the center of statistics and, by extension, science. He helped develop and design the common causal language that is now used by researchers across multiple disciplines. Epidemiology, statistics, sociology, economics, artificial intelligence, political science, they all use the conceptual framework that Jamie started to develop in 1986. So yes, I have several memorable quote Jamie stories, and I know that many of you want to hear them. But let's put it this way: some of them are not commensurate with the quality of this occasion. So I'm not at risk of disappointing you, and to Jamie's relief, I'm not going to tell you about those now. What I'm going to talk, we can maybe talk about that during the reception when people have drank a few true swigs. So what I'm going to tell you today is what happened to me the first time that I met with Jamie as a graduate student. I asked him a methods question that had intrigued me for a very long time, and learning the answer to that question was key for my own research interests. To my surprise, Jamie not only didn't answer my question, but deflected the conversation towards a completely different topic. So I engaged in that unwanted conversation. I mean, what else could I do? But I tried to go back to my original question every time I saw an opening. Nothing. Jamie insisted in talking about something else. And we were playing this game for 45 minutes or so, until suddenly I realized what was happening. The problem was not that Jamie gave me the wrong answer. It's that I had asked the wrong question. And Jamie was patiently waiting for me to realize about that. So I felt very, very, very embarrassed because it took me 45 minutes to see what's going on. And I was also thrilled because I had understood something enlightening. And I was also extremely grateful by how gently Jamie had treated me. And this brings us to to Jamie's unmatched contribution to the teaching of several generations of researchers. The quality of Jamie's one-on-one mentoring is legendary for anyone who have had the privilege of experiencing it. It's really hard to overstate how much one can learn during a 45-minute conversation with him. You enter the room utterly confused, often without knowing it, and you leave with this exhilarating feeling, with this clarity of thought. And in the meanwhile, you have had this intellectual ride during which Jamie has listened to your questions, has challenged your assumptions, has reframed your statement, engaged you in a debate, and flown you to new places that you didn't know that were relevant, but that turned out to be the only relevant ones. And after a quarter of century playing this game, I'm still amazed each time that it happens to me, and inspired each time I see when it happens to others. The only difference is that for me, it takes less than 45 minutes now. And that's because Jamie doesn't teach us only technical concepts. He teaches us intellectual integrity, a logical approach to consider all sides of an argument, to assess an argument on its merits, no matter who is making the argument, to be patient with junior investigators and impatient with arrogant speakers. And if I had to choose just one thing that Jamie taught me, that'd be intellectual humility. Because Jamie has taught us to say, I don't know, when we don't know, and to be ready to admit that we are wrong when we are wrong. There are very few teachers big enough to teach that. So Jamie, thank you, and happy 70th birthday.
That's an impossible act to follow. Well, I don't know what to say after that introduction, but no, I came here like anyone, just finally going to settle some old scores. So it's a little, well, well, I'll just give you the talk I was going to give. There's too much of it, so I'm going to allow voting at various places of which direction to go. All right, so, okay, so I'm not going to say any of this as well as Miguel, but we're in the midst of what Judea Pearl would call a causal revolution. So 40 years ago, different quantitative disciplines had their own language and opinions and idiosyncrasies about causal inference. So philosophy, computer science, artificial intelligence, sociology, psychology, biostatistics, epidemiology, decision science, political science, economics, all were their own little fiefdoms with their own experts in whatever they called causal inference. Today, all these disciplines speak exactly the same language. I mean, that's, I guess, the most amazing thing about that it's really been a revolution. Because of that, we can rapidly learn from each other all the good ideas that different fields had. Actually, there are two apparent languages, not one. One's called causal graphs, And that's people who do almost only that are philosophers, computer scientists, and I guess less sociologists than used to be. Now there are people who use counterfactual models. Counterfactual models is saying I have not only my observed outcome Y, but I think of the outcomes I would have had I received some other treatment. So there's another variable that you don't see. Okay, and statistics and economics use those and hate to talk about graphs. But they are actually one. They are based on the same identical underlying counterfactual model, which I had bad names. So when I wrote this essay, I wasn't an academic. I didn't know anything. I didn't realize there was only one issue in academia, which is to get good acronyms. That your career and whether you're remembered after you're dead depends on nothing but your acronym. So I was just trying to be descriptive. So the causal model I had was called Finest Causally Interpreted Structured Tree Graph Model, which later Pearl renamed an NPSE, Non-Parametric Structural Equation Model, and conveniently has never mentioned the, see, I told you I'm settling some scores, the historical precedents. These actual two different approaches, Miguel mentioned this, is that Thomas Richardson and I made up these graphs called SWIGs that totally usifies them because you can read from the graphs everything, the entire language of the people who use counterfactuals. But I'm not going to show you those graphs today. Okay, so maybe this is a bad choice, as I was going to tell you a lot about what epidemiology looked like when I arrived and got interested in it. And in those days, to recently, epidemiology, the analytic methods in chronic disease, it was all regression. That is, you did a regression model and you put in your treatment you were interested, time dependent or not, and you put in the confounders you were interested in, time dependent or not, and then interpreted regression coefficients as causal if you thought you had measured all the confounders, which for time-dependent treatments turns out not to be the case. But that was back then. But now, because of the causal revolution, there are all sorts of different methodologies from these different branches that cross-fertilize each other. So consider epi and medicine. Now we do mediation analysis, which was a big deal in psychology and sociology back then, though they didn't do it right. There was instrumental variables, which was huge in economics, and there are G methods for time-dependent confounding from EPIs. Also, during the revolution, there were really a handful of people even thinking about causal methods. There are thousands now. I mean, it's a hot topic, and epi, biostat, for graduate students to study, stat, machine learning, artificial intelligence, in fact, all those other fields. And because it's hot, the best graduate students are going into it, and now graduate students for quantitative things are selected from billions of people, not millions. Kids grow up in a remote village in China, and they get picked out and sent to these specialized schools, and they end up here, and they do a lot better than the kid going to Exeter to get here, believe me. So as a consequence, the rate of newly recognized causal problems and new methods to solve them are literally exploding way past anything I ever dealt with some current topics or interference. That's when someone, heard just about that with infectious disease, when someone's treatment has, someone else's treatment affects your outcome. Unmeasured confounding, where there are people are trying to deal with the fact that, let's say, in a large administrative database, all the confounders that you'd like to measure aren't. So you know there are a bunch of unmeasured things, and what are you going to do about it? And there's just weekly one clever idea after another. Again, as I'll discuss later, I'm not sure who's going to win here, and then there's all this stuff called discovery of causal structures, where people have this view that causal effects should be invariant, the size of them and stuff, across different settings. I mean, you can think in genomics, you're hoping the causal effect of something, you know, whether you've done this knockout or this CRISPR or something, there are going to be invariants that are the same causal mechanisms. And people are trying to use that to actually discover causal structure these days. So these are some of the new things people are doing. And there are now too many papers a day to keep up with on the archive, except somehow young people seem to be able to do it. I've never understood it. So now what's driven this rapid development from my point of view? So first, there's been an end of the suppression of causal language when you're talking about observational study in both statistics and medicine. I mean, it's hardly over, but you weren't basically allowed statistics or medicine to even use, as Miguel says, the C word. The internet certainly is making cross-disciplinary understanding and collaboration easy, because you can read anyone's paper at any moment. Causal graphs, which are not, I told you I had this nice new causal graphs, but causal graphs are not something I invented. It goes back to Sewell Wright, but Judea Pearl and some philosophers at Carnegie Mellon really championed this, but they're amazing because they make non-technical people be able to reason causally in very sophisticated ways, where there's an engine they never know about behind this, which is deep mathematics, incredible sophistication, has been distilled into these topological rules for these particular graphs. So people think, oh, causal graphs, these arrows. They're not about arrows. I mean, they are about arrows and causes, but the actual mathematical structure behind them makes it a completely rigorous way to argue. It's, I think, probably been the most potent way that the new causal revolution has been disseminated. And then that there's huge data sets leading to data-driven science rather than hypothesis-driven science. Remember in the early years when people used to say, oh, that's very bad. We shouldn't sequence the genome. What will happen to real science? No one's ever been more wrong, right? Because of this, because it's data-driven, not hypothesis, the latter has made real scientists, not us, but lab scientists, pay attention, because they need causal methods to find those causal SNPs. Gary King, who's in political science here, is a notable pundit, says, more has been learned about causal inference in the last 35 years than in the preceding 2000. And that's an understatement. He actually said 20 years, but that was 15 years ago, so I did the math. Nonetheless, percolation of these ideas into practice can be slow until the untrained old guard move on, they say. You know, the old science progresses one funeral at a time. it's common, yesterday's innovators become today's curmudgeons. It's like often yesterday's left-wingers become today's right-wingers. And one of these innovators recently introduced something, in fact, called the curmudgeon theory of statistics. And I'll send you my paper on it when you want. That's actually true, because I am sort of a curmudgeon. But it is a revolution, but revolutions, as you know, are not necessarily for the best. I mean, we don't have to, we can debate the American Revolution. How's it going right now for you all? And some others. Okay, so there's critiques by the old guard, and so this, so this is the thing. Once you, it doesn't matter how much, you never grow up, you remember the days you had to suffer through, and so I wish I felt about it all the way Miguel does. But, okay, so so part of this is, I want you to know what it was like to be an innovator back then. And it was an unusual one because I also never went to graduate school and I didn't have a mentor. So there was no one who, I was just a random person submitting a paper from nowhere with no degree except an MD. So it took me a long time to get anything published about this except in my big paper, which was published in an engineering journal, because I early on realized the only coin of the realm, the only way to tell you're any good in fields like ours is to reject other people's papers. Because what are we judging on except who got into the American Journal or JASA and stuff? But at least it seemed to me, from the way they treated me, that engineers didn't really care about publishing the paper. They were waiting to see whether you could build something from it. And it was a much nicer culture. So I got a lot of, no one can understand these methods. Now, believe me, this, as I'll get to later, this ain't calculus or general relativity, but I'm just saying that this is what happens usually to new things. And some of the comments I used to get on my paper, early ones, before I could get published, were like, David Cox said it could not be done, this causal stuff. Now, this is not a comment from David Cox. It's somebody who's using his authority to tell me this can't be published. Counterfactuals are unscientific. That's a big one. A lot of people still think that. And the interesting thing is they don't understand it all. This whole theory goes through fine without counterfactuals if you don't want to talk that way, but they actually help. Since that's the way we think about cause, reason about cause, it's very nice to have them, but you can write this whole theory without counterfactuals. The methods are too computationally complex, so I had this method where you had to do a bunch of Mantel-Haenszel tests, 2x2 table tests, but you had to do a whole lot of them. They said, oh, nobody will ever be able to compute a whole lot of 2x2 tests. Prescient, weren't they? Now, of course, I can't believe it. Let's see, I guess I was not allowed to present at the EPI meetings by order of the board. They had a meeting about me, as no one could understand me, so it was a waste. Or maybe it was my transparencies. Were there, I'd have to agree with them. So I can't remember what the real problem was. And, again, not talking about this, but in other areas like calculus and general relativity, it take decades, if not more, for people to learn to simplify the presentation to the point it becomes accessible to high school students or perhaps college students. I mean, general relativity, well, calculus is high school, general relativity is a college course. But causal inferences actually already had its breakout. As I was saying, with DAGs, they have the most beautiful object to explain it that has reduced the most complicated Bayes theorems you've ever seen with hundreds of pages of algebra to like, oh, this line on that graph goes through that node and it's a collider. I mean, it's really awesome. As I said, I had nothing to do with that. And so because of that, like EPI 289, Gels teaches, and 207 I teach, we do very sophisticated causal things to students who don't have to understand the hard math behind them. And many, a lot of people come here, that's not their interest, they're not trained in that, they can do this. These causal graphs are amazing. So, okay, so that was, which was that one? No one can understand. Then the method of, we were just fine without them. So, sure, what you say may be the problem with current methods may be theoretically correct, but in practice not important compared to other biases. We usually get the same people saying we usually get the same answer, and the new methods are harder to implement. To me, I think even were all that true, which I don't think it is, understanding the correct way to think about the relationship of causation to empirical data is valuable in itself. Again, that's exactly the reason causal DAGs have caught on. People really wanted to be able to do that. It's like, also, if justification is the old methods agree with the theoretically sound new ones, then you have to run the new ones anyway, because you got to be sure it agrees in this data set if they're right. But you don't have to rerun the old ones, because you don't have to run them. Anyway, so it's also, for the methods to be taken up, it's important to find areas where the new methods agree with randomized trials, but the old methods don't. And really, these G methods became standard in HIV epidemiology after we, that is Miguel, showed this was the case because of the high degree of treatment by indication in HIV. It's treatment by indication that these methods are especially important for, because they're about time dependent confounders. They're also intermediate variables in the causal pathway. And so like in HIV, something like your CD4 count or your HIV RNA is a huge confounder because it predicts the outcome, let's say time to AIDS. And it's it's a confounder because doctors know that, and that's what they choose to decide to treat on. But a good treatment also influences that. That's the way of treatment works. It either kills the virus and then the virus goes down, the CD4 goes up. So this is exactly the situation that this will be clear as these methods work, and they really made a difference. And so, then the worst criticisms is these methods are damaging the field. Okay, now these are interesting. Okay, so the argument is they take away from time learning, study design, data collection, other statistical methods. I don't disagree. That can be, I mean, not all of these do I disagree with. I don't know if they're damaging, but these are issues. Then there's this graphs replace thinking. Graphs replace biology. We're no longer training scientists, we're training methodologists. What's important is to understand the scientific mechanisms. Well, I certainly don't disagree with that we should learn about biology and be scientists and understand the mechanisms. It's not clear to me that graphs themselves are the reasons that if the old generation think the new ones don't learn anything, as all old generations have always thought, then I would say graphs make all of those things easier to talk about because they help communicate. Then there was an early one. This is the worst thesis ever in the Department of Epidemiology. If that was a student of mine in Miguel's from someone else in the department, even though it was paper was the first, there were these things called representative regimes, it doesn't matter, but it was the first paper about both their identification and application. They're used by many people. Then the more interesting ones, graphs suggest only one way to make causal inference. Causal methods applied to a single study. Well, that's what these often developed for. How am I going to analyze this data if I want to know if something causes something? And so people who say this as, oh, causality is triangulating many different study designs and things, and this precludes triangulation. I don't see why. It precludes that. They cannot be applied to studies of human motivation, for example, or studies of states rather than interventions, like the causal effect of blood pressure or obesity rather than interventions on blood pressure and obesity. Well, to the extent that's true, which to some degree it is, I don't think it's the methods problem, those are harder problems, you know? The hard problems still usually remain the hard problems. Cannot be applied to social epidemiology, social movements, studies of human motivation. Well, it's not as easy, and I wouldn't say anyone's doing a great job of it with these methods or any other method, because those are hard problems. So I sort of think about it. I'm one of those few people who are sympathetic. I'm sure you're all very involved in the debate over string theory. I'm sympathetic to the string theory people. So the critics say it's a scientific dead end. What's come of it over 40 years, same thing, or 35. Stop working on it, you're destroying careers. And my answer is just like, yeah, okay, and do what? I mean, it was the only game in town. Nobody had any idea what to do with that. There was no other decent theory of quantum gravity. It was probably wrong, but to criticize, but not have a better way to show, what does it even mean? So here's a non-leading scientist saying to the leading scientist, hey, you're going nowhere. You're a loser. Yeah, well, who are you? I mean, it was... But unlike string theory, the logic of causal inference is actually mathematical, so it can never be proved wrong. It's just if there are variables that are simultaneously confounders for later treatment, influenced by earlier treatment, and intermediate variables, well, then logically, if you want to know like what you would see in a randomized trial of this treatment, you have to do these things. And that's never going to be wrong because that's actually a mathematical result. It doesn't have to explain nature. And what I like is its very success proves it's ideologically congruent with the status quo. Because it studies only the little downstream tweaks and not the big things. Well, first, if it was so clearly going to be a success and ideologically congruent, why do I have such a chip on my shoulder about the early years? They didn't seem to. But at the bigger issue, in some sense, I agree. You all were at, I gave another sort of old man talk a few years ago called How I Became My Mother, which, since my mother's already been mentioned without my permission, I believe that I better explain this because it does relate to these things. I was she was an epidemiologist, and she used to study antisocial personality, and in particular studies like, what was home life when you were small? Did that lead to you being antisocial, going to jail later? And she was good level. She was studying it, though, in the Black community. And she would get results like, if the father's not in the home or something, maybe there was a relative risk of 1.7 stuff. And I just looked at her as a teenager. I said, what are you doing? I mean, it's like having somebody on the rack breaking their back, a bunch of people, and saying, how are we going to predict which one's back is going to break first? Instead of saying, well, why don't we take them all off the rack? I mean, and that's the sense in which people are criticizing it. And I think in a sense that's true, but that's again, the limits of often what you can do with what we know how to do in epidemiology, at least yet. I'm not saying there aren't going to be clever people coming up with clever things, but right now we need sort of people like each other, but for exposure. And it's pretty hard to, say what it would be like if, using epidemiology, to say what it would be like if, this social class and racial bias of this country suddenly went away, So, okay, it would be nice to do that, but I'm not sure I know how. That wasn't the problem I thought I could solve. It's like once you're successful, you're supposed to, it's your problem, you haven't solved every problem. But I'd like someone to solve it. It ain't going to be me, or at least not yet. So then, it's already 4:45. Well, now it's time to start choosing. So I can tell you more stories about epidemiology in the old days. I can never, I don't really know. Here, we will, I'll do this, and then I'll maybe skip to the end. Okay, so how I got into this, I had a college friend, Mark, and we started an occupational health clinic at Yale when we were medical residents there in 1979. And we were working with trade unions to contest the company doc and promote occupational health and safety, so we had to testify often. And whenever we testified, we were asked, is it more probable than not that the worker's, let's say, lung disease was caused by his exposure at work? Which obviously led to being interested in causal inference. And scientific papers consisted mainly of epi and biostatistical analyses, so I enrolled in some classes and quickly learned in biostatistics, this was in the old days, causation was a dirty word if it didn't come from a randomized trial, randomized clinical trial evidence. But of course, for ethical reasons, nobody was randomizing harmful chemicals. So it was pretty hard to disentangle from their point of view causation from spurious correlation. In an epi, the meaning of causal statements, causality was allowed, but this pretty much, not always, but things were pretty well, not very well formally defined. So I got into this because two problems caught my attention. One was the bias due to the healthy worker survivor effect, which biostatistician Ethel Gilbert explained in an article Without a Solution. And think of an occupational mortality study where the outcome is death from chronic obstructive pulmonary disease. And you get data on when and if the worker if and when the worker dies of COPD. You get data on whether a worker has left work or still works. You get the dose of exposure to the chemical under study in the particular job they're working in, and you get no other data beyond demographics. So individuals who leave work receive no further exposure. That's what it means to leave work, you have no more exposure. But they're also at greater risk of death from COPD because some of the individuals leaving work have unrecorded COPD. That's why they left. But we don't have data on that, only deaths. So leaving work is a confounder for the effect of subsequent exposure because, leaving work causes your next exposure, determines whether you leave or not, determines your next exposure and your outcome. So we have to adjust in the analysis for whether you're on work or not. But exposure may be a cause of leaving work. That is, leaving work may be a proxy for an unmeasured intermediate variable, the COPD, on the causal pathway from early exposure to death. So if you adjust for it, you might block that pathway and therefore underestimate the effect because we want the total effect of what's going to happen to you if you're exposed to this much of the chemical. So that's this classic situation where you have something that changes over time, whether you're at work, and it's a confounder for later exposure, but it's caused by the early exposure and maybe an intermediate variable in the causal pathway. And then, in this case, regression adjustment fails whether we put work status as a time-dependent covariate, even if there's no other unmeasured confounders. We have all the data we need. It's just we got to do the analysis right. So that got me interested in that problem. And the story with treatment by indication is the same thing, which is now everyone knows. It's called personalized or precision medicine. You want to know how to treat the patient. You have observational data, let's say from electronic medical records. You'd like to figure out what's the optimal CD4 level to start. And it's the same problem. Doctors are more likely to give treatment to ill patients so that even if the death rate in the treated is greater than the untreated, treatment could be good for every individual because they're treating people already so sick that they can't undo that, but they could prolong each person's treatment, could prolong their life. That is, association's not causation. And if a doctor just noticed that fact, that if he treats people, they die earlier and withheld treatment, that's called a malpractice suit. So the epidemiology has some things. And it's a difficult problem for the same reason as before. Those getting more treatment have worse health status. And so health status and predicting death and the later treatment, but CD4 and the covariate here is not leaving work, but your CD4 and HIV RNA count, which predicts how you're doing with the virus, but CD4 and HIV are affected by beneficial earlier treatment, so it can be on the causal pathways. So here I was going to show you how causal graphs immediately allow you to see these things in a way that back then I had to explain them with logic and equations, but I don't think we're doing, you aren't going to get any pictures. I've already sort of said that. Okay. I'm not going to do any of these pictures. So again, beat a dead horse. Back in those days, so, I was taking Epi and biostat courses. And first, at the time, most textbooks in Epi were called Intro to Epi, which was a strange field. And books either did not address time-varying exposure, or did so under the assumption there were no time-varying confounders affected by earlier treatment. So none of the books had anything to say about this. So, I don't know what to do. Well, this is relevant to Miguel's gracious introduction. So one thing I was thinking when I was giving this, it would be difficult to give a talk about a field that one's ideas have had a big impact on, because you either proclaim a special talent for oneself or you try to be self-effacing by saying you are a one-eyed man in the land of the blind. which can be insulting. But where else are you, what's the other move? I always some combination, but I lean to the latter. Why is that? So this is here. So people with formal training in mathematical reasoning, like myself, I was a math major in college, were, unlike now, not going into EPI in the early 80s, with the exception pretty much of my long-term friend and close collaborator, Sandra Greenland. So without such training, it's hard to formalize intuitions in a rigorous way that allows one to see exactly what assumptions are needed and to work out the mathematical implications of these assumptions. You have to know math. I also had a further advantage. I just had finished a medical residency, had no contact with the orthodox ways of thinking in biostat or epi, and yet was well aware of the real world problems that needed solving, since both fields in their different way had gotten confused about things. It was probably lucky I hadn't heard about the confusion. And since, about the other thing, I've worked with a huge number of people who have much more logic and mathematical talent than I, but I was the one-eyed man, one-eyed person. This is, okay, I'm gonna forget that. That'd be fun. This is about all these, okay. The future. And if you're interested in staying after whatever, 5 or 6 or 7, I could go back to the rest of it. Okay, so first I have to say, because you're supposed to talk about what's going to happen from here, and so and the usual line, it's hard to make predictions, especially about the future. So I think there already is some huge work on studying so-called interference in social network, how you hear or you tell your friends and it's passed along and you send the tweet to someone else. So it's clear, I think, without quantitative, Facebook and social media have served as a major fuel for authoritarianism, fake news, and in fact, genocide around the globe. And so we need to understand how it works and what interventions may affect it. And I'm sure that research will be done, but it may be used for evil or for good, because once people, if they succeed in figuring out how to manipulate people better, that's what it means to be able to intervene and make these things less bad, they may want to make it worse, depending who they are. Another big thing we've heard some about today, so I'm going on, leaving that sort of sad state of affairs to go on to another one, is how to integrate machine learning and artificial intelligence with causal inference. It's a big topic on Twitter, I've seen. Everyone knows it's important. Few are sure what it means. So one of the issues that comes up, and this is connected, is there are big data sets with, we know there's unmeasured confounding because the data was not collected for research purposes. And so the question becomes how to adjust for unmeasured confounding, which is clearly impossible without assumptions, because you can't, that's the whole point of observational data. You can never tell whether it's confounding or not, given the things you measured. So there are recently many proposals by both statistical people and computer machine learning people that some are incredibly carefully thought out, incredibly ingenious and creative, others not so much. But it's a kind of interesting thing. I think it has to do with how many people are trying to solve the same problem of causal inference from medical data, but there's either, you would say, an embarrassment of riches or an embarrassment of garbage, because there are so many things coming out. It's clear that, as we've seen recently, and there's a discussed paper coming out in JASA, that better mathematical understanding would have helped a great deal. But the final question is, which assumptions are best? Well, since we have to make assumptions, there's no a priori way to say which are best. So the natural thing is to, have some sort of empirical, comparisons, like compare, you think there's, with randomized trials of the same thing to see if one of these methods do better. Or take data sets where you do have what you think are most of the confounders and throw out some of them, give them to these people to run their methods, and see who gets close to the analysis that use the confounders and so forth. But this is, I think, a huge interest to people, and it's something that, as I've learned recently, something that people do machine learning, deep learning, are really, it goes with the way they think about the world, which is reducing the dimension of the problem. So you sort of create the confounder from the exposures. And this is a way they do a lot of things, not in causality, that work for prediction. So they're hoping it works for causality. And I don't know if it does, and it's not going to be easy to find out, and there are going to be many proposals. And its future is pretty murky to me, but it's really important. Then there's the thing I always think about, Tianchi was sort of talking about, is what about, are we going to go towards rational medicine where we randomize every patient or every clinic visit for every treatment that's not that's inequitable, like what people don't know. I mean, that would be, it would be massive and need everything Tianchi talked about, plus a lot more. Integrated databases, automatic analyses. That would truly be the integration of AI and causality. You can see I'm discussing these at a much less nitty-gritty level than the previous speakers. Well, then there's, so let's see. Causality in genomics, we've heard about that today. ALKEs and other biological measurements. And then there's this issue that a lot of people are getting into again, invariance of causal effects and heterogeneous background. It's a new idea about actually, it's not, the idea that causal effects should be somewhat invariant, but actually how to do it in data analysis and stuff. Like, as I said, if you have lots of different knockouts or CRISPR misspelled experiments, or also many cities, and hope for invariances in some causal effects, even though we realize, so the idea is you realize across cities or something, it's just the opposite thing. There's no reason to think you're not gonna have confounding between cities. But what if you found something that was invariant in all these different environments to some extent? Can you leverage that backwards? So you can think of this as, well, let's put it this way. It's not like people are trying to answer the kind of causal questions we're answering in FE studies. It's some bigger game to try to think how to reason about this complex world with these complex data sets and so forth. And I have no idea whether this kind of thinking could go anywhere. But boy, as I say, they're amazing people in the field. The originality of their ideas, formally, logically, mathematically, are really wild, and it's pretty cool, but who knows? I think that's all I have about that. Oh, and I have to do my shout out. Let's see. So, as I said, causal methods research is now an acceptable way to make a living. And there are huge advances by many grant students I mentor and advise. So I'm going to give my shout out only, since they're younger ones, but only to the ones who are already, household names in this field. So there's Tyler, and he's done. So these are all kind of a lot of it, especially Tyler and Eric, research way beyond, things I've tried. This is what I'm saying. It's the future. So he's worked on a lot of interesting topics. Miguel is the person making all this available to the world. As far as I can tell, he is teaching 4 courses in 4 different continents at every moment. And he's, as well as doing 40 actual analyses and writing 9 editorials. And I don't understand how any of my students get that much done. And then, this is still on Miguel. Implicate development causal methods in many areas of medicine, public health. He's really, I think, in the public world, if anyone changes the world, it'll be Miguel. And there's Eric, who I have to say, I think, blows my mind. I think he's just the most creative person in this field I've ever seen. He has really deep new ideas almost every day in so many different areas. And then Beth Halloran, who is much longer ago than these, who has done a lot on infectious disease and interference. And so I guess what I'm saying is, I don't know the future. Ask these people. Okay, I'll stop.
Do you allow us to ask questions or comments, make comments or so?
You can do anything you want.
Please.
As long as you don't mention my mother.
That's in your mouth, yeah. Indeed. Please, go ahead. Yes, Tyler Vanity. Tyler, please.
Jamie, thank you for a wonderful presentation. Thank you for your countless contributions to the field. I do want to thank you also personally for your teaching and your mentorship, which has done so much to me over the years. And as I think you have rightly indicated, you've made all work in this area much easier to carry out. You've really paved the way for all of us. I'm deeply, deeply grateful for that. To illustrate one of Miguel's points as well, as a very short antidote on one question on confounders that Jamie and I went back.
You meant anecdote or
and couldn't quite come to an agreement. Jamie then sent me a long email with a Socratic dialogue between epidemiologist 1 and epidemiologist 2. And that turned out to be completely sufficient to resolve absolutely everything. I did want to pose a question, a 2-part question. The contribution of how to deal with time-dependent confounding was extraordinary. It's really empowered the field. And it was a difficult problem. One question that I've sometimes pondered is, what would have happened if you hadn't come to epidemiology? How long would it have taken us to get to this insight? Would we still be in the dark on this? What would the field look like? I realize it might be difficult to speculate on that particular counterfactual, but it has for me been an interesting one. And then relatedly, is there something equally deep that we are currently missing?
I told you where my money was. Go cash it in. That was a counterfactual question, which are very hard to answer, as you know. I think, who knows? I mean, it could have been very short time because of the interactions with the internet in 10 years after that. Certainly in terms of the bully pulpit, Judea Pearl, the Turing Award winner, is biggest, but The question is, if he hadn't met people like me and Sander, would he just be continuing to do search and never gotten into any of the search means going from association to causation, and never gotten into this interacting with, this field, or who knows what he would have done. But yeah, so I have no idea.
Thank you. Michelle?
So Jamie, thanks. That was just remarkable, and we could have spent another 4 hours going through all those slides. And I'm sure, pretty sure, with a certain degree of certainty that almost everyone would be sitting here listening. But I wanted to pick up on Tyler's point, because as you were presenting your remarkable talk, 2 people came to mind as I was playing through a counterfactual model. One of them was a former chair of epidemiology who was also a Cutter lecturer in 1982 by the name of Demetrius Chakopoulos. And something about you giving this lecture reminded me of a role, a causal role that Demetrius played in this exercise we're all experiencing. And then there's another non-epidemiologist that I will mention during this celebration of epidemiologists, and that is former Dean Barry Bloom, who I think played a very big role in many of the names that you gave acknowledgments to. And so I just wanted to ask if you would reflect on the role that some people played at particularly important tipping points in your illustrious career.
Well, first, about those 2 in particular, I wouldn't be here if it wasn't for Demetrius. That he used to have this 11-year rule, which I guess is essentially 8 now. And I was in one department that fired me, and I was also in biostat, and they fired me. So I was about out the door. At that time, I'd been here 10 years and had exactly 1 publication in what's considered a legitimate statistical journal. I hadn't been very successful. So, so then I went to Demetrius, and I said, would you tenure me and keep me here as your methodologist? And he said, oh, sure.
That's right.
And then as I was leaving, and he was incredibly gracious. I mean, it was amazing. As I was leaving, though, he turns to me and says, there's one thing I need to know. Do you understand logistic regression? If you want to say that's like tenuring someone in math at Harvard saying, actually, do you know addition? It was pretty funny. And then Barry Bloom, Dean, was a huge supporter of mine, because as you could tell, I needed some support. And when there was this chair position, he made sure that I talked to Mitchell Dong, the donor, and basically, I think, greased those wheels, so I got a chair. Now, if you all don't know, at this point in history, having a chair at the Harvard School of Public Health plus $8.95 to get you a cup of coffee. You get nothing from it, but then, I mean, since people don't, I might stop there because people don't know all the, all my collaborators and stuff who I would feel I'd have to mention first and tell you how great they are and what they meant to me, but it won't mean anything to you because you don't know.
Seems a very good moment to stop, but before that, I want to give you something.
Oh, yeah.
This is the plaque. And this is the photo op. I give it officially to you.
Okay,
Jamie,
what do I do?
thank you, first of all, for your A very enjoyable, inimitable 170 Scott lecture. Thank you very, very much. And now I invite you all to go upstairs. We have a reception there, which is also the holiday party start for the Department of Epidemiology, but for others as well. I invite you there. Thank you.